Section 13.4, motion in space, is velocity and acceleration. So we've talked about velocity and acceleration in Calculus 1. Also, a lot of you have had physics. So it probably goes without saying, but just as a quick review, when we have a position function, s of t, so the t here is specifically denoting time, that velocity at time t is v of t, and that's the first derivative of the position function. So here we're treating t sort of like an x and not necessarily a parameter t. Acceleration at time t is a of t, which is the first derivative of the velocity function, and that translates as a second derivative of the position function. So another thing, remember when we say speed, specifically it kind of means velocity, but technically it's the magnitude of the velocity. Alright, so what this section's about is looking at this from the perspective of vector functions. So now we have, let's say, a position function that is a vector function, r of t, just like we've had in this whole entire chapter so far. So let's just say now specifically it's mapping a position as a function of time. In t, the parameter is specifically time. Then, just with that little twist there, little details added, then our derivative, by definition here from section 13.2, is specifically a velocity vector with respect to time. So exact same definition here. The derivative of the velocity vector, I didn't say that right, the derivative of the position function or the vector function is the velocity vector function. Wow, a lot of terms thrown together there. So here's the exact figure from section 13.2 again, just as a reminder here. Now specifically r prime of t is also denoting v of t, where v is a vector, denoting the velocity vector with respect to time. Okay, so moving on. Let's talk about or revisit speed. So speed is still the magnitude of velocity, but as a vector, that's going to take a slightly different form. It's not going to be a matter of just you get a negative answer, make it positive, as we had in Calc 1, but now rather when we talk about vectors, we talk about magnitude in this sense, where you're going to take the derivative of each and every component with respect to t, and then the magnitude would be each of those squared added up, take the root. To make things even a little bit more confusing, why not? In this section of this book, and also pretty standard across different books and in courses and whatnot, we now use the script v or cursive v, the same one that we used for velocity in Calc 1, is now going to denote the magnitude or speed, the magnitude of the velocity or the speed. So, or in other words, r prime of t with the magnitude here. And I missed my bar here, but I'm going to not put it on there because I realize now that it makes all my little white boxes for the rest of the document end up being behind the text I'm trying to hide. So I'll just hold off on that. Anyway, so let's just get our hands dirty with an example here. Consider the position function r of t, and we're given this in component form. T squared minus 4 in the I or the x direction, and then plus tj, which would be in our y direction. So here this is in 2D, but it's written parametrically as a vector function, so that part is new in Calculus 1, 2, and 3 sequence anyway. This is something you do in physics and possibly other classes. But anyway, part A, find the velocity and acceleration vectors as a function of time. Part B, find the velocity and acceleration when t equals 0 and t equals 2. Sketch the position plane curve and show the velocity and acceleration vectors at t equals 0 and t equals 2. And finally, find the speed of the particle at t equals 2. So we got a lot to do. Part A, find the velocity and acceleration vectors as a function of time. all you need to do is take the derivative of r of t. Remember, we do that component by component, and that would be the velocity. Acceleration, you take that answer and take the derivative of it. So A is not too bad, and this is our result. Derivative of t squared minus 4 is just simply 2t, so that's in the I. Derivative of t is 1 in the j. Acceleration, taking the derivative of that, we're going to get, for the derivative of 2t is 2, and the derivative of 1 is 0, so that component ends up going away. Alright, we're on to B. Find the velocity and acceleration when t equals 0 and t equals 2. So we're going to use our answers from part A and just plug in t equals 0 and t equals 2. And so we get those results. Finally, or not finally, but next we have sketch the position plane curve and show the velocity and acceleration vectors at t equals 0 and t equals 2. So this is something we've done in this chapter already. It's not absolutely necessary, but this is what you can think of as a parametric equation in vector form. And so if you can eliminate the parameter t, then it's easier to draw the xy curve. And it's xy because we have an I and a j component here. So for this one, we notice some things. First of all, it's helpful to realize what component goes where. So the y is t, and the x is t squared minus 4. So it's easy to relate t to y, and then simply plug that into the t over here in the x equation. So putting that together, we get x equals y squared minus 4. And that's advantageous because this is a curve that's easy to draw. So you could orient your axis either way, but if we do it with the y being our vertical axis, we have a parabola. So next, t equals 0 is an equation. At t equals 0, we need to find the point that goes with that. It's actually something we kind of did up here. Oh wait, no we didn't, never mind. Anyway, just plug in your t equals 0 into your x and y components and you get the point -4, 0. We're tasked with also sketching the vectors representing the velocity at t equals 0 and the acceleration at t equals 0. And so I just wrote these again down here, and then going ahead and doing that, we just do our vectors from the point at which we're interested in. So for this one, again, we're looking at -4, 0, which is right here, and that actually can help you just even sketch that curve too. And so our velocity vector is just 1 unit up, and our acceleration vector is 2 units in the j, or in the I, excuse me. 2 units in the x, or 2i. So do the same kind of thing at t equals 2. So the point that corresponds with that, just plug in that t equals 2 into each of the little equations for x and y in the position function. So you get 0 and 2, which is up here. And then, again, we already calculated our velocity at 2 and our acceleration at 2. So just drawing those vectors from that point, notice that the acceleration is exactly the same. And then for our velocity vector, we're going to go 4 in the positive I, or positive x direction, and then we're going up 1 in the j, or in the y direction, and then we can draw that vector in blue. So finally, just a little follow-up question at the end. What is the speed at t equals 2? And so in vector land, we need to make sure we're taking the magnitude, which involves taking each of the components here, squaring, adding, and taking the square root. So that answer ends up being square root of 17. So I'm going to stop the recording here, and then I'll pick up with another recording for the next part.